In the world of quantum computing, raw data isn't enough. Before a quantum computer can solve problems, it must first understand the data, not in classical bits, but in the language of quantum states. This transformation is called quantum encoding, and it's the very first step of every quantum algorithm. In this video, let's discuss about quantum encoding and different quantum data encoding techniques. Today, we are going to discuss about introduction to quantum encoding, why quantum encoding is needed, types of quantum encoding, quantum implementations, and circuit diagrams. What is quantum encoding? It is a method of representing classical or quantum data within the state of quantum system, typically qubits. In classical systems, the data is stored as binary bits, either 0 or 1. The quantum system's information is stored in qubits, which exist in superposition. A bit can only exist as 0 or 1. But a qubit can exist in superposition of both 0 and 1, represented as a point on the block sphere. Unlike a bit, a qubit's value is not fixed until it is measured. Its exact state collapses to either 0 or 1 upon observation. Why quantum encoding is needed? To leverage on quantum parallelism is to process multiple states simultaneously due to superposition. It is also used in quantum algorithms. Quantum algorithms begin with initializing qubits in an encoded state, rely on encoded data for operations like interference entanglement. Such algorithms are Grover's algorithm, quantum Fourier transform, variational quantum algorithm. What are the types of data we use in daily life? To convert any classical data into quantum state, we must first express them in numerical form. Numbers. It is already in numerical form. Text. We can use ASCII or Unicode encoding for different languages other than English. Let's take an example as A. ASCII value of A is 65. In string hello, each character is mapped to its ASCII value and presented as a list of numerical values. Image. We take pixel values. Images is a matrix of pixel values, right? So we these pixel values are already numerical. In grayscale image, we have one number per pixel. This is the intensity of or brightness. RGB. In RGB image, we have a particular value for red, that is one value, and green and blue. So we'll have three numbers per pixel. Audio and video. Audio can be sampled into amplitude values, which are numerical. Video is again a sequence of image frames. Images are a bunch of pixel values which are numerical values and can be encoded. Now let's see types of quantum encoding. We have three types of quantum encoding. They are basis encoding, angle encoding, and amplitude encoding. First, let's see about basis encoding. It is the simplest form of encoding. Classical binary bits are directly mapped to quantum basis states. That is, if there is a bit 0, then it is represented as get 0. If there is a bit 1, then it is get 1. If there is a binary number 0110, it is directly represented as 0110 in quantum states. And if there is 101, it is directly represented as get of 101. So, total number of qubits required are nothing but the number of bits in the data. So, if we have 4 bits, we'll need 4 qubits to store the 4 bits of data. So, here the pros are that it is simple and intuitive, but it requires 1 qubit per bit. It is easy to implement, but it is not effective for large data sets. So, let's look at an example 3, 5. What is 3 in binary number? That is 011. So it can be represented as get 0, get 1, get 1. And 5, 101. So it can be represented as get 1, get 0, get 1. And 1 comma 2, 1 is get 01 and 2 is get 10. They can be represented as 0, 1, 1, 0. This is how we represent in basis encoding. Now coming to amplitude encoding. Amplitude encoding is a method where classical data is encoded into amplitudes of quantum states. We know that in a quantum state psi, assuming it has n qubits, it will be represented as this. So here A is amplitude, I is basis state. So we also know that the quantum states are always normalized, that is, sum of squares of amplitudes will be always 1. So the data becomes amplitudes of each basis state in amplitude encoding. Let's see for 1 qubit. We can represent that the basis states are 0, ket 0 and ket 1. So we can represent two datas, A0 and A1. So for two data values, we need 1 qubit. For 2 qubits, we'll have 4 basis states 0, 0, 0, 1, 1, 0 and 1, 1. We can represent 4 data points as we have 4 basis states. So we'll have 4 data values for 2 qubits. Now for 3 qubits, we can represent 8 data values as we have 8 basis states with 3 qubits. So we can say that for 2 power of n data points, we need n qubits. For 2 power of n data points, we need n qubits. Now, can we directly insert data values as an amplitude? No, because quantum states are always normalized. That is, if we are representing quantum state as like this, we know that sum of squares of amplitude is always 1. So the data also must be normalized. So what are the points to remember from here? Data is stored as amplitudes of quantum state. For 2 power of n data values, we need n qubits. Amplitude of data is always normalized. This is amplitude encoding. Now let's see an example. If we are taking x as 4 data points, first we need to normalize the data. That is, gives us root 15. And we need to represent them as amplitudes. So 1 by root 15, comma 2 by root 15, comma 3 by root 15, and again 1 by root 15. The values are 0.258, 0.516, 0.774, 0.258. We have 4 data points. So we have 4 data values, that is 2 square data values we have. So how many qubits? 2 qubits are required. So number of qubits are 2. The basis states will be 0, 0, 0, 1, 1, 0, and 1, 1. We'll be representing them, these data values we got as amplitudes. So 0.258 plus 0.516 into base state 01 plus 0.774 base state 10 ket 10 plus 0.258. This is the quantum state we have after encoding it with amplitude encoding. Now let's try this example. Here we have only 3 data values. So we need to take the nearest power of 2. Here we have 3. So what is the nearest power of 2 which is greater than 3? That is 4. So here also we'll need 2 power 2, that is 2 qubits. First step, normalization. Root of 2 square plus 1 square plus 3 square, that will be root 14. And the amplitudes, after calculating amplitudes, there will be 2 by root 14, 1 by root 14, 3 by root 14. That's it. What will be the values of them? After calculating the values, 0.267, 0.5374, 0.801. So because we are taking two qubits, we'll have four basis states: ket 00, ket 01, ket 10, and ket 11. So these will be the amplitudes. We have three amplitudes. So fourth amplitude will be 0, 0.267 plus 0.534 plus 0.801. So this is the quantum encoded state after encoding with amplitude encoding. Now let's look at angle encoding. Encoding classical values into qubits using rotational gates that rotate the qubit on Bloch sphere. This uses Rx, Ry, and Rz gates to encode values as angles of rotation. The data value here becomes the angle in the rotation. Default value starting position is ket 0, then the rotation is applied unless and until any gates were applied previously. These are the rotation matrices for Ry, Rx, and Ry and Rz respectively. Now let's look at an example. Here, let's take the data value as 1.5 and let's apply Rx gate. So the data value is 1.5. We are applying 1.5 as theta and we are substituting in the given matrix. We'll get the following matrix as a result. We know that the starting position is always ket 0. So we're going to multiply with the Rx matrix we got with ket 0 and we'll get the following result as the angle encoded value. Now let's look at pros and cons of angle encoding. This will work well with the continuous data. This is used in quantum feature maps in ML, quantum neural networks, quantum variational algorithms, and all. But it can only encode only one value per qubit. So it is not that efficient compared to amplitude encoding, but it can be used in multiple use cases. Not suitable for encoding large vector compactly. Sensitive to gate noise when it comes to hardware. Now, let's discuss about the implementations of above techniques. First, basis encoding. We know that the qubit default value is ket 0. So, whenever the data is 0, we can keep the default value. But whenever the data is 1, we need to flip the default ket 0 to ket 1. We know that poly X gate is also known as bit flip gate. So, whenever 1 comes, we can use poly X gate to flip the 0 ket to 1 ket. Let's consider the data we have is 10. The binary representation of 10 is 1010. Now, this has 4 bits. So, we are initializing 4 qubits. That is 0, 0, ket 0, ket 0, ket 0, and ket 0. Now, the data is 1, 0, 1, 0. So, here this ket 0 should be flipped to ket 1. And this 0, whenever this 0 is here, this should be ignored as it is. And then again 1. So we need to flip this ket 0 to ket 1. And here again 0, so we ignore this part. So polygate is applied in here and in here. So whenever the data is 1, we apply polygate. Now let's see code. I've written a function with a number as a parameter. Here, in this case, I'm passing 12 as the number. So, first 12 is passed. What is the binary number for 12? That is 1100. And here we have 4 bits. So, we have to initialize quantum environment with 4 qubits. So, I'm initializing quantum environment with 4 qubits and then drawing the circuit. We know that we need to apply poly X gate when the data is 1. So when the data is 1, I'm applying poly X gate. So the output will be ket 1, again X gate, normal, ket 0, Nothing here also gets 0. So here, whenever the data is 1, I'm applying poly X gate and then returning the circuit. In the circuit diagram, as you can see, we applied first two poly X gate, then I ignored the rest two. Because the data is 1, 1, 0, 0, we need to apply poly X gate when the data is 1. Now let's talk about amplitude encoding. First, we need to observe the data, that is, if the data length is 2 power of n, we need n qubits. So we need to observe the data length and then identify number of qubits it requires. And then normalize the data. Then create the quantum environment with qubits and then introduce the normalized data as amplitudes. Let's talk about amplitude encoding code. We have vector of length 4, that is 2 square. So we need 2 qubits. So I'm initializing the quantum environment with 2 qubits and then initializing the vector, normalizing the data. In amplitude encoding, we know that the normalizing data is a very important step. And then in the circuit, we already have a predefined method called amplitude embedding with the parameters, features, wires, normalize. Features is nothing but the data we are passing, that is normalized vector, and wires are number of qubits. And then as we normalized previously, we don't need to do it again. So I'm passing the value as false and then drawing the circuit. Now I'm also printing the normalized vector, which is same as the calculated value previously. And then in the circuit, we have 2 qubits as we took 2 qubits. In here, I am applying amplitude encoding. Now, for the basis states, you can see the respective amplitudes. For 00 ket 01, ket 10, and ket 11. These are the respective amplitudes. Now, let's look at angle encoding. We know that in angle encoding, for n data values, we need n qubits. So, according to the data length, we'll first decide on how many qubits required and then map each data point to the rotation angle. And then we need to choose gates either Rx, Ry, or Rz. And then apply rotation gates to initialize qubits. And then we have quantum angle encoded data. Here, first I'm just doing the data, one data that is 1.5. So I'm initializing the quantum environment with 1 qubit and then I'm applying Rx gate, right? In the circuit, I'm passing one parameter as I only have one data and then applying Rx gate and returning the circuit. Here I'm applying the circuit, drawing the circuit. I'm also drawing the encoded values in here, print the state. So I'll get the result as this. This is what we calculated previously. And then this is the circuit. In the circuit, we only have one qubit which has a Rx gate. So this is the output. That's it, guys. Thank you. So, to wrap it all up, quantum encoding is a critical bridge between classical and quantum world. It allows us to take real world data like numbers, images, or signals and map it into quantum states that we can process on a quantum computer. We have seen why it's needed. Without encoding, we can't even begin quantum machine learning or quantum simulations. We have seen types of data, types of encoding, basis, angle, and amplitude. Basis encoding is nothing but representing the classical data in form of quantum states directly, mapping the classical data directly to quantum state. Angle encoding is nothing but applying an angle theta of rotation on data. Amplitude encoding is nothing but representing the data as an amplitude of basis states. So, if we have 2 power of n data, we'll need n qubits. And we have also seen implementation and circuits for the techniques discussed.
Like and subscribe for more quantum computing videos.